All right, welcome back to Statistical Analysis in Psychology. This is week 15, class number 2, and today is when we are going to take a look at our final hypothesis test in chapter 10, and that is the analysis of variance. So this is an extremely powerful, very multivariate type of hypothesis test that can be used for a number of different types of situations. We're going to focus on just one of those as a sort of introduction to the analysis of variance. But I'm very excited about this one because this is the statistical test that I use most often in my research. So it's very powerful. It's very important for psychology, and we'll see why in just a moment. But this is going to be our final hypothesis test. So congratulations, we've made it to the end. Time to finish strong on this, our 8th day of the face-to-face shutdown. So let's head into Anova territory now. With an example that we're going to draw from a new area of psychology, animal psychology, something we haven't talked about too much before, studying animals simply for the sake of understanding the behavior of animals. So we are going to turn to a very weird behavior that birds do, which is migration. So migration is something that we've come to accept. We see the birds migrate every single fall. We see them come back every single spring. Sometimes when the world is a little turned upside down in terms of its weather, the birds get confused and we see them migrate at different times. But migration in and of itself, when you think about it, is bizarre because these birds are traveling phenomenal distances. So the one that travels the most is called the Arctic tern. And this bird literally travels from all the way at the top of the northern hemisphere all the way down to the bottom of the southern hemisphere. So that's the red line that you see on your map. And other birds don't migrate quite so far, but as you can see, they're still migrating massive distances. So we have some birds that undertake this phenomenally difficult journey as part of their instinctual behavior. What makes it really confusing or mysterious is that some birds do this, but other birds don't. So we have birds like blue jays and birds like cardinals that do not migrate. Birds that somehow are able to survive in the winter and don't have to resort to such a massive undertaking, such a dangerous journey in order to survive the winter. So why is it that some birds don't migrate, other birds do migrate? Well, we're going to take a look at data based on a study that took a look at the brain size of birds and actually tried to link migratory behavior with intelligence. And the question that they were asking was that if you take a look at the relative brain size of birds and use that as a measure of intelligence, if you actually take a look at bird brains and use that as a measure of intelligence, are the birds that don't migrate simply more intelligent than the birds that do migrate? Is it the fact that these birds are migrating as a last resort because they lack the intelligence in order to survive the winter, whereas birds with bigger brains have more cognitive skills, more cognitive tools, and they are better able to survive the winter? They can store food, they can remember where food was stored, they can come up with strategies for surviving the harsh winter months. So is it the idea that birds that don't migrate, they don't do that behavior simply because they're more intelligent, and birds that do migrate just lack that intelligence in order to survive in a winter environment, and so therefore need to resort to these oftentimes massive migratory journeys? So that's the question we're going to take a look at today. And we're going to see that the way that the experiment was set up required a new hypothesis test to be used. So we're going to see first why a t-test would not work in this particular situation, identify situations where you're going to need an ANOVA, and then we're going to introduce the idea of ANOVA so that it can sink into your mind. And then next class, we're going to take a look at how to actually do it in SPSS. So today, as I mentioned, we'll just introduce the need for ANOVAs. We're going to take a peek behind the curtain, take a look at the logic of analysis of variance in terms of a hypothesis test. What are we actually analyzing? I know it's there in the title. We're analyzing variance, but what does that actually mean? So we'll peel back all the layers so you can see the inner workings of the machine, and then that'll prepare you next time to plug it all into the machine and learn how to do it in SPSS. All right, so first off, the introduction here. So far, every single hypothesis test that we've been doing has had a similar structure in the sense that every single one has been taking a look at two populations. So we would take a look at population number one versus population number two. Is there a difference between the two populations? And depending upon the type of setup, we would basically take a sample from population number one, and we would take a sample from population number two, and then we would do a hypothesis test based on those samples to see if we could conclude that the populations were truly different, that the means of the populations were different. And this kind of setup has served our purposes this far. However, this isn't every single question that is asked in science, and especially this is not every single question that is asked in psychology, because whereas a lot of questions are between two populations, such as the population that takes a drug versus the population that is in a control condition, or the population that receives therapy versus the population that does not receive therapy. Whereas a lot of questions are, is it this one or this one? Many other ones don't just have two alternatives, but have more than two alternatives. So what can we do if all of a sudden we don't want to just know, is there a difference between two populations, but is there a difference between three populations, right? So what if we're asking a question about drug A, drug B, and a control group? All of a sudden we have three populations, and that type of a question comes up in psychology all the time. So what we would do, first step, is what we've been doing all along. We would take a sample from that third population. So we would need to take a sample from that third population because, again, population number three, unknown, we don't know anything about it. But we can identify individuals from that population, and we can take a sample of those, and we can measure that. So where do we go from here? Well, let's reorganize these so the populations are in order. So we got population 1, 2, and 3. And we'll get rid of the unknown populations so we can focus in on the samples because, again, that's all that we have access to. And what we're going to do first is we're going to show what we cannot do, what is incorrect to do, what can lead and has led to incorrect conclusions being made that have harmed people, harmed psychology because it was done incorrectly. So this is the thing we do not want to do. And I'm pointing this out because oftentimes this is where our human minds go to. Because as critical thinking scientists, we're oftentimes looking for solutions using the tools that we already have. So you might take a look at these three samples here, and you might say to yourself, well, if it was just sample 1 and sample 2, I would do a t-test. And then I could tell if population number 1 and population number 2 were different. So that t-test on sample 1 and sample 2 would tell me if population 1 and population 2 were different. So maybe, and this is wrong, I'm just showing you, maybe the next step would be to test population 2 and population 3, right? So if I test sample 2 and sample 3, I could determine if population 2 is different from population 3. So maybe apply a second t-test. And then to complete the analysis, maybe I do a third t-test to see if population 1 is different from population 3 by testing sample 1 versus sample 3. So maybe the way that we could solve this question here and do this hypothesis test is to simply do what we were doing before and just do multiple t-tests. Do multiple t-tests on every single pair combination, and maybe that would be the way to analyze this hypothesis, to do this hypothesis test. Well, as it turns out, that is incorrect. That is wrong, and there is a serious problem doing it that way. So what is this problem? Why is this not allowed? Why do we need a new technique for this new situation? The reason is because doing these multiple comparisons, doing 3 comparisons for one hypothesis test, what that does is it inflates your experiment-wise alpha level. Alpha level is your probability line in the sand. It is a line in the sand that you set in terms of how improbable you're going to allow your sample to be before you reject the null hypothesis. So that line in the sand, that alpha level is key. Remember, it's alpha. Alpha does not, you do not change alpha until you have way more letters after your name. Alpha is alpha. It got the first letter in the Greek alphabet. That's how important it is. So we want to make sure that the alpha that we're using, that experiment-wise alpha, stays the same. And that's the alpha for the entire experiment. Now, we're going to introduce two kinds of alpha terms. There's experiment-wise alpha, and then there's test-wise alpha. And experiment-wise alpha is your alpha for the entire experiment. Test-wise alpha is your alpha level for each comparison. Now, we haven't brought this up until now because usually in our experiments up until this point, we've only had one comparison, right? We've had two conditions. You want to tell the difference? You have one comparison. Two samples. You want to see if the populations are different? You have one comparison. So up until now, your experiment-wise alpha level and your test-wise alpha level was the same because there was only one comparison. But your test-wise alpha level and your experiment-wise alpha level change once you have multiple comparisons, and that's the key to the problem. Because this test-wise alpha level, that's your type 1 error rate. That is how much you are willing to risk saying that something is there when it's not actually there. Saying that populations are different when they're not actually different. That's how much you're willing to risk accepting the research hypothesis when you should have accepted the null hypothesis. So saying that there's a difference when there's not there, you're always going to have that possibility, but usually we say the most we can tolerate is 5%. That's as high as we can go, so we set alpha to 5. That's what we want to do. We want to maintain that alpha level. Your experiment-wise alpha level, though, that's your accumulated alpha level from all your comparisons. So we have an accumulated type 1 error, an accumulated probability of incorrectly saying that something is there, that a treatment is effective, that the null hypothesis is rejected, when in fact nothing is there, the treatment is not effective, the null hypothesis should not have been rejected. So let's see the effect of multiple comparisons on a test-wise alpha level and what it does to your experiment-wise alpha level. So to make this a little bit easier, we're going to start off with a contrived example, and then we're going to put some more realistic numbers on it. So bear with me for this one. So consider a test-wise alpha level of 0.5. And this would be the situation if you had a statistical test, and your statistical test on whether you accept or reject the null hypothesis was you simply flipped a coin. Because an alpha level of 0.5 means that you have a 50% chance of saying that there is an effect when in fact there is no effect. That's what the alpha level means. So what that means is that if you were just flipping coins to test your experiments, you would have an alpha level of 0.5. That would be your alpha level. So that's what we're going to do. And I'm choosing this because we're all familiar with flipping coins. So it's a nice way to illustrate this effect on test-wise alpha level. So for this analysis, let's suppose that there is no effect. What that means is that population number 1, population number 2, and population number 3 are all the same. There is no difference. There is no effect. So what's the probability, given our coin flipping statistics, what's the probability of making that type 1 error? What's the probability of saying, yes, I found an effect, when in fact there is no effect? So what's the probability of making that error after one test? Well, the probability of that is the same as the probability of flipping a coin and getting tails. So we're going to call tails the incorrect answer, right? Tails is where we reject the null hypothesis, so that's an error. So what's the probability of making an error when you're comparing sample 1 to sample 2? Well, it's a 50% chance. And that is completely fine because we might flip the coin and get the right answer, heads, and we'll say, oh, okay, there's no effect. But we might flip the coin and get the wrong answer, tails, and conclude incorrectly that there is an effect. We have a 50% chance of making an error after one test. But guess what? That's fine in this situation because we want our experiment-wise alpha level to be 50%. That's what we decided prior when we said, all right, let's choose an alpha level of 50%. So after one test, we're fine. We're exactly where we want to be. We're willing to tolerate a 50% chance of making a mistake, and we have a 50% chance of making a mistake. So far, so good. That's only after one test. We still got 2 more tests to go. So what happens to our probability of making at least one error now after 2 tests? Well, this is where it gets a little bit more complicated, a little bit of a wrinkle in there, because now in the second test, we have a 50% chance of making an error as well. So in this case, we have a 50% chance of making an error on the first test. We then have a 50% chance of making an error on the second test. So we could make an error on the first test and an error on the second test. That's one combination with at least one error. We can make an error on the first test, but not on the second test. That's a second combination with at least one error. We can make an error on the second test, but not on the first test. That's the third combination. And the only way we avoid an error is to not make it on the first test and not make it on the second test. That's only one combination. So we got 3 combinations, 3 possible outcomes where we make at least one error. One combination where we don't. That means that our error rate has ballooned from 50% to 75%. And that's a problem because we want our alpha level to be 50%. We're willing to tolerate that much risk. But now because we've made that second experiment, we've gone to the well once too often, we've risked it once too many times, and our risk level, our actual alpha level has ballooned now to 75%. And the biggest problem now is that we're not even done. We still got one more test to go. So now that we made a third test, once again, we have a 50-50 chance of making an error on that third test. So now there are 8 combinations in total of outcomes that could occur, and only one of them, where you flip heads, heads, and heads, only one of them out of 8, we don't have an error. Only one of them we don't make an error and say something is there when it's not there. So our alpha level of 0.5 of 50% has now ballooned to 87.5%. And that's only after 3 tests. If we had 4 tests, 5 tests, that would just keep ballooning and ballooning to the point where we could make serious errors, and we would be highly likely to conclude that something is there when it's not there. And that is dangerous, to conclude that a treatment is effective when it's not actually effective, to conclude that there is a difference between populations when there's not actually a difference between population. That can fuel all sorts of problems. That is why we need a new way of testing. Now, you might be saying to yourself, well, that's if we choose an alpha level of 50%. We've never even gotten close to an alpha level of 50%. And in reality, an alpha level of 50% is ridiculous. So let's put a less ridiculous number on it. Let's take a look at an alpha level that we've all used before, an alpha level of 0.05. And we can think of this, just to kind of keep the metaphor going, we can think of this as flipping a really unfair coin. A coin where you have a 5% chance of it coming up tails and a 95% chance of it coming up heads. So this is like a weighted coin, a completely unfair coin. So once again, let's do our analysis and suppose that there is no effect, no difference between population number 1, population number 2, and population number 3. Now that we're using a real world, real life alpha level of 0.05, an alpha level of 5%, we have basically said we are willing to risk a 5% chance that we will say something is there when it's not there. And that's the most we're willing to risk. That's our line in the sand, 5%. That's the biggest risk we can take. What happens if there is no effect and we go in there with an alpha level of 0.05? Well, once again, if we're only doing the one test, then we flip our coin. We got a 95% chance of making the correct conclusion that there is no effect, but we got a 5% chance of making the incorrect conclusion that there is an effect. And that's not a problem. Again, not a problem after one test, because that risk level of 5% is exactly what we determined we were comfortable with. We wanted an alpha level of 5%. The actual risk level is 5%. We're good to go. That's after only one test. Problem is, we got 2 more tests to do. So what happens after the second test? Well, again, we got a 5% chance of making that error on the first test. We then also have a 5% chance of making that error on the second test. And when you do the math, of what's the probability of making an error on the first test, and then follow that up with what's the probability of making an error on the second test, as it turns out, our alpha level of 5% that we were comfortable with has now ballooned to a level of risk of 9.75%. It's almost doubled. And when you're dealing with people's lives, when you're dealing with the psychological effects that we are analyzing statistics to deal with, that's a huge problem. That our risk has just almost doubled after only 2 tests is a huge problem already. And it gets worse because we have 1 more test to do. So once again, 3 tests, we got to go 1 more time. We got to flip that coin 1 more time. Once again, we have a 5% chance of making an error on our 3rd test. And now our risk level that we were willing to accept of 5% has almost tripled to 14.3%. So while we were willing to tolerate a 5% chance of saying an effect is there, when in reality it's not, we're in actuality having a 14.3% chance of saying that an effect is there when it's actually not. So this is something that has actually happened in the history of psychology. This is not just a theoretical exercise. This is something that has actually happened in the history of psychology. And a famous example of this was a study that was done in 1964, and it was the analysis of the MMPI, that's the Minnesota Multiphasic Personality Inventory, profiles of 40 college-educated overt male homosexuals. So these researchers, Dean and Richardson, they were trying to study, are there any personality differences between heterosexual males and gay males? So they gave the Minnesota Multiphasic Personality Inventory to 40 gay males, and they analyzed the differences to their to the heterosexual control group. Now, the thing about the Minnesota Multiphasic Inventory, the Multiphasic Personality Inventory, it's in the name, it's multiphasic. It takes a look at multiple dimensions of a personality. What that means is that if you're going to compare the gay group with the heterosexual group across multiple dimensions, you're going to make multiple comparisons. And as you can see in the table here, they used a t-test. So if you take a look at that final column there, you can see t-statistics. So they did multiple t-statistics on each of these different dimensions. So these are the dimensions here. And as you can see, the ones that are significantly different, possibly incorrectly significantly different, they're noted there with an asterisk. So I've highlighted them here as well. So gay males were found to be significantly different in this study from heterosexual males in terms of psychopathic deviant, in terms of masculinity, femininity, in terms of schizophrenia, and in terms of hypomania. So how excitable are they? Odd thinking and social alienation, masculinity, femininity, stereotypical male or female interests and behaviors, psychopathic deviant, conflicts, drug or anger, lack of respect for society's rules. So the problem here, though, is that there was multiple comparisons being made. So the probability of finding a difference when a difference didn't actually exist ballooned in this study. It ballooned. It went past the 5% that they were willing to entertain. So when they found these differences, when they found these significant differences, it was way beyond the probability that they were willing to entertain. So unknown to them, they were hoping for a 5% risk of finding something when it actually wasn't there, concluding that there was a difference when it actually wasn't there. But that ballooned after 9, 10 comparisons. I don't even know, I haven't done the math. I don't even know what that balloons to, Remember, 3 comparisons ballooned to over 14%. So the chances that at least one of these 4 differences, maybe all 4 of these differences, was incorrect, was not an actual real difference, the chances of that are high. And you can imagine, just imagine the damage done back in 1964 when this analysis came out, and it was determined by psychology research that gay men score higher on being psychopathic deviates, right? That gay men score higher on being schizophrenic, right? Just imagine the damage that that would have done in that time. And you can see the importance of making sure that we use the right statistical tests in the right situation. So a t-test, wrong test for this particular situation. So what do? Well, we need a new way of doing these tests. And what we need to do is we need to find a way to make these multiple tests, because as psychologists, we want to do multiple tests, right? It's not right to say, well, I guess we can't take all the personality dimensions. Let's just do one. No, we want all 10. We want to take a look at all 10. We want to be able to ask questions that compare multiple populations or multiple causes. So we need a new method. And that's where the Anova comes in. It's a way of making multiple comparisons without inflating that alpha rate, without getting that alpha level out of control. So the way that it does is, it is a single test that uses one alpha level to simultaneously test all of the means. So instead of doing one by one comparisons, it does all of the comparisons all at once. Seems a little bit like a little mathemagic, but we'll see exactly what it does, and hopefully it'll make sense in just a little bit. Now, before we get to the Anovas, we need to talk a couple of terms before we get there, just so that we're aware of which of the many Anovas we're going to do, to end this course this semester. So the first thing we need to do is we need to talk about factor. And factor is a term that simply stands for the independent or quasi-independent variable. This is the cause that you're testing. So we call it a factor when we're looking at Anovas. So you can have one factor, one cause that you're testing. You can have multiple factors, multiple causes that you're testing. In psychology especially, multiple causes are usually what is tested because we're very complicated behavioral entities. So we have the factor, that's your independent or quasi-independent variable. That's the cause that you're testing. We then have levels. And the levels are the individual conditions that make up your factor. It's the individual values that your factor can take. So let's take a look at a few examples so we can put some context on this. So in the Harlow infant monkey study, the infant monkeys were placed in cages with 2 artificial mothers. One of them was made of soft terry cloth. The other one had a wire mesh body, but it had a bottle from which the monkey could feed. So in this experiment, there was one factor. There was one cause that they were looking at, and that was the type of mother. Wire mesh mother or terry cloth mother. Which mother would be chosen? And you can kind of see from my hand gestures there. In terms of the levels of that factor, there was only 2. There was a wire mesh mother and there was a terry cloth mother. Now, if they added a third type of mother, if they had a wire mesh mother, a terry cloth mother, and a water balloon mother, I don't know, then that would be 3 levels. But as it is, we have one factor, type of mother, that's all that we're looking for, and we got 2 levels, wire mesh versus terry cloth. And if you have one factor and you got 2 levels, that's a t-test, and that's when it's appropriate to use a t-test. All right, let's take a look at another example. When people learn a new task, their performance usually improves when they are tested the next day, but only if they get at least 6 hours of sleep. That's good psychological advice. All right, so the following data demonstrate this phenomenon. The participants learned a visual discrimination task on one day and then were tested on the task the following day. Half the participants were allowed to have at least 6 hours of sleep, and the other half were kept awake all night. So hopefully you've automatically kind of analyzed this and realized that we have half of the participants are getting 6 hours of sleep. Another group, a separate group of participants, is not getting 6 hours of sleep. That's two separate subjects measured once. That's an independent means t-test. But importantly, it is a t-test. And the reason for that is we have one factor in this experiment, and that is the amount of sleep. And then we have two levels, which is you either get 6 hours of sleep or you get no hours of sleep. If we added in a third amount of sleep, so if it was no sleep, 3 hours of sleep, or 6 hours of sleep, that would be 3 levels. We would still only have one factor, but we would have 3 levels. Let's take a look at another example. Strack, Martin, and Stepper reported that people rate cartoons as funnier when holding a pen in their teeth, which forced them to smile, than holding a pen in their lips, which forced them to frown. This is a test of one of the bizarrest theories I've ever heard in psychology, which is the facial feedback hypothesis for emotions. And the idea is that your mind figures out what emotions you have by reading your face. So it's a complete inverse of what we intuitively think. We think that we feel the emotion in our mind, and then we send signals to our face to express that emotion. So we're happy, we're sad, we change our muscles depending on our emotion. This facial feedback hypothesis hypothesized, and there's a lot of support for it, hypothesized that when we experience an emotion, our faces change, and then our mind reads our face and says, oh, I'm smiling, I guess we're happy. Oh, I'm frowning, I guess we're sad. And this is why sometimes if you are having a bad day, just simply smiling will make you feel better. Just simply changing your body into an upright posture will send messages to your brain that says, you know what? Your body is acting happy. Your face is acting happy. I guess you must be happy. So anyways, half of the people rated the cartoon with a pen in their teeth, which forced them to smile. The other half rated the cartoon with a pen in their lips, which forced them to frown. A researcher attempted to replicate this result using a sample of 16 adults between the ages of 40 and 45. For each person, the researcher recorded the difference between the rating obtained while smiling and the rating obtained while frowning. So once again, hopefully your mind is automatically getting to the point where it says, all right, one group of subjects measured once while smiling, measured a second time while frowning. That's the same people measured twice. That's a dependent means t-test. However, for our purposes right here, importantly, we got one factor in this experiment, which is facial expression. What's the effect of facial expression on the emotions you're feeling? And we got 2 levels, smiling versus frowning. So once again, the appropriate test for this would be a t-test. 1 factor, 2 levels, you're going to go do a t-test. However, let's say that we read this experiment and we said, you know what, that's very interesting, but I wonder if it's affected by age. I wonder if it's affected by, cognitive development. So let's say that we investigate that by seeing if this facial expression effect works the same for children versus young adults versus old adults. So we set up the exact same experiment and we tested on children, we tested on young adults, and we tested on old adults. What's the design now? Well, now we've added a second factor. Now we have 2 causes that we're looking at. Factor number A is still facial expression. Factor B now is age. So now we have 2 potential causes, and we have 2 levels for factor A. So facial expression can be smiling versus frowning. But now we have factor B, and we got 3 levels. We got children versus young adults versus old adults. And in this situation, t-test is not going to cut it. A t-test is inappropriate for this particular situation. So what are we going to do? Well, we're going to turn to Anovas. And as you can kind of see, Anovas take the situations where you have more than 1 factor and or you have more than 2 levels. And there are multiple ways to combine all of that into multiple different types of Anovas. So to end our introduction to statistics, we're going to focus on the simplest Anova just so that we can introduce this idea so that we can become familiar with Anovas, because they are a very important hypothesis test, and you will learn about all the other Anovas when you go to grad school and you take your statistics course at that time. However, this is intro to statistics, so let's finish with our intro to the Anova. So we're going to consider the simplest Anova. We're going to consider the single factor independent measures design. So this is an ANOVA that has one factor. It's got one cause. What makes it different than a t-test is that it can have as many levels as you want. It can have 3 all the way up to 3 million. It can actually have all the way up to infinity if you want to get technical, but it can have as many levels as you want. So that's what we're going to take a look at. And importantly, this is an independent measures design. So the subjects that get level number 1 are different from the subjects that get level number 2. And they're different from the subjects that get level number 3. And they're different from the subjects that get level number 4, all the way up to the final set of subjects who are different from everybody else, and they get your final level, level K. So we need to set up this new ANOVA, a new hypothesis test. And one of the first things we need to do is we need to come up with new ways of expressing the null and the research hypothesis. Now, as it turns out, this is going to be pretty straightforward, starting with the null hypothesis. So the null hypothesis is simply the logical extension of what we've been doing before. The null hypothesis is the hypothesis that every single population mean is equal to each other. So the mean of population number 1 is equal to the mean of population number 2, which is equal to the mean of population number 3, which is equal to the mean of population number 4, which is equal to the mean of population number 5. And we keep playing this game all the way up to the mean of population K. So that's the null hypothesis. That's what we've been dealing with up until this time. The means of the population are the same. So that's just simply an extension of what we've been working on up until this point. The difference, though, comes in the research hypothesis. And the research hypothesis is the complete opposite of the null hypothesis. So that's the same, but there's a little bit of a wrinkle here because the complete opposite of all the populations are the same is that at least one population mean is different from the others. So they could all be different from each other. It could be that half of them are different from the other half. It could be that there's just one population mean that is separate from the rest. Whatever it is, the null hypothesis is the complete opposite. Takes into account all the other possibilities not covered by the research. The research hypothesis takes into account all the possibilities not covered by the null hypothesis. And in this case, the null hypothesis says everything is the same. The research hypothesis says at least one of them is different. Maybe they're all different, maybe just a few of them are different, but at least one of them is different. Now, because of this, we're going to express the research hypothesis as an English sentence. Because at least one population mean is different from another is very difficult to write mathematically. Because you would have to write that the mean of population number 1 does not equal the mean of population number 2. And or the mean of population 1 does not equal the mean of population number 3. And or the mean of population number 1 does not equal the mean of population number 4. And or the mean of population number 1 does not equal the mean of population number 5. And you would keep doing that all the way up to the mean of population number 1 does not equal the mean of population K. And then you get to start it all over again with population number 2. The mean of population number 2 does not equal the mean of population number 3. And or the mean of population 2 does not equal the mean of population 4. And you would just keep doing that for every single possible combination. So you can see, way easier to simply write that out in English. At least one population mean is different from another, and know that it includes the and or of every single population could be different from any other population mean. Doesn't have to be, but it could be. And at least one of those is different. At least one of those is not the same as the other. All right, so let's now take a look we've taken a look at the hypotheses for the ANOVA. Not surprisingly, we need a new test statistic. So the test statistic for the ANOVA, it kind of works like a t-statistic, and it works kind of conceptually like a t-statistic. Because what a t-statistic is, in its essence, in its sort of boiled down basic analysis, what a t-statistic is a measure of the obtained difference between two sample means. So what was the difference between the sample means that you measured in your experiment? And then you divide that by the standard error, and that's the expected difference. So how much difference could you expect if there was no treatment effect? And then what was the difference that you actually found? And that's why bigger t-values usually led to the rejection of the null hypothesis, and smaller t-values usually led to accepting the null hypothesis. So the t statistic was always, what's the difference that you found versus what was the difference you would have expected if there was no treatment effect. That's the t statistic. Your test statistic for an Anova is like a t statistic, but instead of using mean differences, it uses variance. So it takes a look at the variance between the sample means and then divides that by the expected variance. So it takes a look at the variance between all of the sample means and then divides that by the variance that you would have expected. So much like a t statistic, it is what did you find versus what did you expect to find. So an f statistic now is variance. What did you find versus what did you expect to find? And the f there, you might be wondering, f for Anova, what's going on here? The f there is for Fisher. So this is called the f test or the f statistic, and it was named after Fisher, and we mentioned him way back in our first class at the beginning of the year. All right, so that's the f statistic, and that's what we're going to be searching for, calculating in order to do our hypothesis test. All right, so now that we know that we're going to be dealing with an f statistic, now that we know that we're dealing with variance, we're going to take a look at exactly what variance are we analyzing. So it's an analysis of variance. What is the variance that we're actually analyzing? So let's put some numbers on these samples so we can see what we're talking about. So sample number 1, 5 subjects. We measure these 5 subjects, and their scores are 0, 1, 3, 1, 0. So let's just say that we give them a quiz. We give them some sort of personality test, and it's out of 10, and they score 0, 1, 3, 0, 1, 3, 1, 0. Those were their scores. So that's 5 subjects. We then take a different set of 5 subjects. Remember, these are independent means. We take a different set of 5 subjects from population 2, and we give them that same test, and they score 4, 3, 6, 3, 4. And then we finally take 5 different people, this time from population 3, and we give them the test, and they score 1, 2, 2, 0, 0. So we have all of these scores now, and we're going to do an analysis of variance on these scores. And now the question we're going to ask here is, what variances are we analyzing? And as it turns out, analysis of variance analyzes 3 sources of variability, 3 sources of variance. And the first one that it analyzes is total variance. And that is the variance for all the scores. So if you forget about the fact that these samples come from different populations, and you just throw them all together into a big, huge jumble of 15 scores, notice that those 15 scores are not all the same, right? Some of them are 0, some of them are 3, some of them go as high as a 6, you go as low as a 0. We got 15 scores that have variability. So the total variance is simply the variance for all 15 of those scores. And you can think of that as the complete amount of variance in your experiment. That's the total variance in your entire experiment, because out of all of your 15 scores, that's how much variability you have when you consider all of those scores together. So that's total variance. That's the first type of variance that we're looking at in our analysis of variance. Second type of variance is between treatments variance. And this is the variance among the treatment means. So if you take a look at our 3 samples, you can see that we've calculated the means for these 3 samples. And we have the mean for sample number 1 is a score of 1. The mean for sample number 2 is a score of 4. And the mean for sample number 3 is another score of 1. 1 and 4 are different. There's variance there. So the between treatment variance takes a look at the difference between the means of these samples. How much difference is there between these samples because of the treatment, right? What did the treatment do? Coming from different populations, what does that do? That variability is measured in the between treatments variance. And then the last type of variance that we have, the third type, is within treatment variance. And this is the variance within each treatment. So this is the variance within each sample. So if we take a look at sample number 1, we got 5 people there. and they didn't all score the same score, right? There's variability there. So within treatment variance would measure that variability, comparing those 5 to each other and calculating variance for that sample. And then within treatments variance, we do the same thing for sample number 2, comparing those 5 scores to each other. And it would do the same thing for sample number 3, comparing those 5 scores for each other. So within treatment variance, looks at the variance within each treatment, the variance within each sample. And as it turns out, once again, by a little bit of mathemagic, it turns out that total variance equals your between treatment variance plus your within treatment variance. So those 3 sources of variance break down in this relation where all of the variance, your total variance, equals the variance between your samples plus all the variance within each specific sample. So how are we going to use this to compare the population means? How are we going to use this to compare and see if these populations are different? Well, it boils down to what is causing, or what are the potential causes of each of these types of variance. So between treatment variance, where does that come from? What are the potential sources of between treatment variance? And the potential sources of this are the treatment effects and random variation. So when you take a look at the mean for sample number 1, and the mean for sample number 2, and the mean for sample number 3, let's focus in on the mean of sample number 1 and the mean of sample number 2. The mean of sample number 1 is a 1. The mean of sample 2 is a 4, right? 4. The mean of sample 2 is a 4. There's a difference there. Why did that difference occur? Well, one possibility is treatment effects. One possibility is that population number 1 is actually different from population number 2, and that's why we have a score of 1 versus a score of 4. So that's possible. That's possibility number 1. It's treatment effects. The other possibility is that it could be due to random variation, right? It could be due to the fact that we chose 5 people from population number 1, and maybe we just happened to get 5 weirdos, weird and wonderful people from sample number 1, right? From population number 2, we got 5 other people that had their own kind of characteristics and issues. So it could just be that there was just random variance, and that's the reason why we have a score of 1 for sample number 1 and a score of 4 for sample number 2. So this difference that we find could be due to an actual real difference, treatment effects, or it could just be due to random chance, that random variation. So that's where the between treatment variance could come from. The within treatment variance, however, loses one of those sources, and it specifically can only come from random variation. And the reason for that is because it looks at the variance within each sample. So in sample number 1, those scores of 0, 1, 3, 1, and 0, they're different from each other. But their differences cannot be due to the treatment because they all received the same level. They all came from the same population. They have all been treated the same. So there's no possibility that their differences in their scores in sample number 1 amongst each other is due to a treatment effect because they were all treated the same. Same thing for sample number 2. All of the people from population number 2, all of the people in sample number 2 were treated the same. So the fact that one of them scored a 4 and the other one scored a 6 cannot be due to a treatment effect because they were treated the same. And the same goes for sample number 3. So within treatments, the variability that we see within treatments, that can only come from random variation. That can only come from the chance effects that different people will score different things at different times. That can only come from random variation. So what we do then is we use that within treatments variance as our measure of the amount of random variation that we could expect. So going back to our formula for an F statistic, we have the variance between the sample means that we found, and we have the variance that we would have expected. So the variance between the sample means, we just did that, we just looked at that, that can come from treatment effects, or it can come from random variation. So whatever score we get for the variance between sample means, that can come from treatment effects or random variation. The expected variance, on the other hand, the variance that we would expect if there was no treatment effects, that can only come from random variation. And notice that now we have in the numerator treatment effects and random variation. Those are the two sources of between treatment variance. Random variation in the denominator, that's the source of within treatment variance. So the F statistic becomes between treatment variance divided by within treatment variance. And when we measure the between treatment variance, we know how much variation we found. And then we divide it by within treatment variance to figure out, and that within treatment variance is how much variance should we have found. And then we analyze the F statistic that results from that division. So what is that F statistic going to look like? We're going to wrap up today by taking a look at what exactly is the effect of this treatment effects and random variation on your F statistic. So let's put that F statistic up there. And let's start off with no treatment effect. So what does the F statistic look like if the null hypothesis is true, right? There's no treatment effect. Well, if there's no treatment effect, then in this equation here, we can set treatment effect equal to 0. That's literally what no treatment effect actually means. So if we sub in 0 into this equation, we see that the F statistic equals 0 plus random variation divided by random variation. 0 plus random variation simply equals random variation. And hopefully you recall that random variation divided by random variation, anything divided by the same number is going to be equal to 1. So when there is no treatment effect, the F statistic is going to be equal to 1, right? It'll be, so the F statistic will be equal to 1 if there's no treatment effect. So that's if the null hypothesis is correct, is true. What about if there is a treatment effect? Well, if there is a treatment effect, that's like saying that the treatment effect is greater than 0. So what happens when we put that into our F statistic equation? Well, let's call this greater than 0. Let's symbolize it by x, right? So we'll put in the variable x. So your treatment effect equals x, however big x might be. So the top part of the numerator becomes x plus random variation. Denominator is random variation. We're just going to do a little bit of algebra here to kind of break this down a little bit. So we split it up. So it becomes your treatment effect x divided by random variation plus random variation divided by random variation. And we did this because we don't know what x is. We don't know how big that treatment effect is. But we do know that part of the equation. And that part equals 1. So we are starting with 1, and we're adding some extra value to it because of the treatment variation. And because of that, if you have a treatment effect, your F statistic will be bigger than 1. So that's kind of the bottom line in terms of how an F statistic works. No effect, it'll be equal to 1. The more effect there is, the greater than 1 your F statistic will be. So we're going to end today with a quick look at the F distribution, just to kind of give you one last kind of tie back to our traditional ways of doing hypothesis testing, because it really is just another form of hypothesis testing, so the logic still applies. So when we did the T statistic and the T tests, we took a look at the T distribution. We're now doing an Anova, we're doing an F test, so we're going to take a look at the F distribution. So on the x-axis there, we have the F statistics, and then on the y-axis, we have the frequency with which they occur. First thing you'll notice is that this is a positively skewed distribution, so it's not symmetrical, but it still works like a distribution. So we're still going to choose an alpha level, and that alpha level is going to define a line in the sand that's going to split our distribution into the body and into the tail. So if we have an alpha level of 5%, we are going to choose a line that cuts this distribution and puts 95% of the distribution in the body and 5% in the tail. That is still the critical region. And then what we're going to do is we're going to take a look at all of our samples. We're going to run an we're going to run an Anova. We're going to calculate an F statistic, and then we're going to find out where that F statistic is on the distribution. And just like we've been doing the entire semester, if our F statistic is in the body of our distribution, we're going to accept the null hypothesis. However, if our F statistic crosses that line in the sand, if the F statistic goes into the tail, then we're going to, like we've been doing so far, we're going to reject the null hypothesis. So that again is the basic idea of the analysis of variance. exactly like we've been doing so far with the T-statistic, just now a new test for a new situation. So that's what I wanted to cover today. Next time we're going to see how to do this with SPSS, but kind of let that sink in. Maybe watch this video, a couple of more times, just so that you're really clear on the situation that we're analyzing. Because next time we're going to take a look at how to do this in SPSS, and we're going to take a look at how to do the complete analysis, so that any sort of situation that you want to take a look at that has any number of levels, you will have the skills and the tools to do it correctly, to do it right, not to inflate that error rate, not to put people's lives at risk, put psychology at risk, but to choose the right statistical test for the right situation. And we're going to do that when we learn how to do Anovas next time. So that's it for today. Thank you so much for joining me on this week 15 class number 2. We're going to meet next time for a look at how to do Anovas in SPSS. But for right now, that's all I wanted to cover. So thanks for joining me. Stay safe, and I will see you next time.